So we look at the application of partitioning. So the true application of partitioning constant, the partition constants that we looked at, it will become more obvious when we start doing transport, but for now we will look at something very simple, which and we will explain that why this is not relevant in its state in which the way in which we define it, but it is very useful in getting some basic information from contaminant fate transport point of view. At least you will know some very crude information from these kinds of analysis. Okay. Now we will expand on this and go, when we go to fate and transport, this will become very useful there. Okay. So for example, let us take a very simple example that I have a system. So I am not going to use systems like soil, sediment and all that, because it is very impractical. So let us say I have a system of a closed container which has some soil or sediment. Now let us say which has some solids which is similar to soil and sediment, and let us say we have water. Okay. We will start with these two systems first as of now, then we will move on to the third one. Okay. Now into this system I will add, let us say I will add 100 kilograms of some chemical A. So what do we mean by adding 100 kilograms away is, say there is a contamination, there is a pollution problem. So somebody dumps 100 kilograms away into a water system which contains air, water and solids, okay, into the system. It is a very straightforward problem, but what we are going to look at is some of the calculations that we will do. So the question that we will ask is, the following. And the solids. Or in other words, what fraction, other forms of this question, what fraction of A will end up in water or the solids. Okay. So similar to what we did in the last class for the measurement of partition constant, we are redoing the same thing, but with our focus is different. Here we are looking at how much of a particular chemical will partition into which phase, where will it be. So essentially we are asking this question. So we are saying, so I need to define this system. The system is, I am just given some rough information. More information I need about the data that I need is the following. One I need is the volume of water, V of 2, let us say it is 10 raised to 3 meter cubed, 1000 meter cubed, okay. So it is a million liters, 1000 meter cubed. I also have M of 3, mass of 3, the solids is also, let us say it is 10 raised to 3 meter cubed kilograms. I have an additional piece of data. So this is what we call as wet solids. So right now, as I have drawn the diagram, it looks like it is sediment, the water on top of other than solid, which means the entire solids are water saturated. So I have to give you what is the porosity of the solids with its water content. So theta, which is the moisture content, let us say it is 0.5. So the definition of moisture content, you have to be very careful, different definitions of moisture content people use. So So, in this particular problem I am using moisture content as mass of water over so let's we'll call it as M3. Let's not worry about M2 plus M3. We'll just say M3. So, what this means is that it's mass of water over mass of wet solid. So, you have to be very careful here. Whenever definition is done of moisture content, this is one way of doing it. The other way of doing this is mass of water over mass of dry solids. Okay. And there is a reason why people use dry solids as a reference, because dry solids is absolute. Wet solids need not be wet, because the way we measure wet solids, suppose I want to measure moisture content, I have to go into this layer, take out a sample of water. By the time I am analyzing it, it may not have the same moisture content as what it is there in situ. So, things are very difficult to determine in terms of as a reference. So, we are saying moisture content as a reference, the denominator is some solid basis. So, the wet solid is here what we are talking about. M3 is the, we will call it as M3 dash or M3 dry. Yeah. So, the dry plus the water is what we are calling as M3. Sometimes M3 is just dry solids, that is whenever the problem changes we will look at that as well. So, this is somewhere you have to be careful, because this affects the mass balance and all that. So, the calculations will change based on this. So, you have to be careful in the way this is defined. So, right now in this problem we will talk that M3 is wet solids, yes, and the moisture content is 50.5 on the basis of wet solids. So, you can directly calculate. So, if this is wet solids, you know how much is the water content here. Yeah. The other data that I have continued is A, pertaining to A. This chemical, the log KOC of A is 4.0. Let me give you that. The aqueous solubility of A, let us say, is 1.0 milligrams per liter. Okay. This is the aqueous solubility of A. The other additional data I have is the Henry's constant is 0.003. This is a ratio of rho A1 over rho A2. This is the ratio of concentrations. This is the definition. I can have other definitions of Henry's constant. We will, but this is common in environmental literature. So, the other definition of Henry's constant could be the concentration in the gas phase can be expressed as vapor pressure, partial pressure, whatever is the vapor pressure of the. So, there is confusion over vapor pressure, partial pressure and all that. We will clarify that in a minute. So, that is Pascal, okay, and the water concentration is mole per meter cube. This is one way of doing it, or you can have grams per meter cube, either of these things. You have moles per meter cubed or grams per meter cubed. These units are commonly used. Okay. So, in case you see some of these other units in literature, you have to convert from there to here. So, using ideal gas law and all that. So, we will not do this in the class. I will not give you Pascal per meter cubed and all that. We will stick to whatever is the ratio of concentration. But in general, when you are looking at data or problems outside in this field, you may have to deal with units like this. So, you have to convert them into common units. The units are a big problem. So, they are all over the place, they are not the same system. You have to make sure we are in the same system, and then mass balance will work out nicely. Otherwise, you will make errors and numbers will be 1000 times off sometimes, and that will cause major problems. Okay. All right. So, here that. Then we also have additional data about the soil sediment itself. we need FOC, fractional organic carbon in the solids. So, let us say it is 0.2. 20% of the solids is fractional or is organic carbon. So, this is one definition that we have. The particle density, which is rho of 3, particle density, which means the density of the solids, average density of the solid also I am giving you, it is, let us say it is 2300 kilograms per meter cube. Okay. Done. So, we write mass balance. What is there initially? Initially we are doing mass balance of A in the system. So, mass balance of A in the system is initial, and what we did in the calculation in the last class for the partitioning, we are doing partitioning. The assumption in partitioning is when we say partitioning constant, we are saying it is at equilibrium always. So, initial, and then we are saying that at equilibrium the total amount of A is conserved, nothing is happening to it, it stays as it is. So, what is the total amount of A initially? It is 100 kilograms. This is what you are adding into the system. So, 100 kilograms of A is present, you are now putting it into your system, and then you are seeing where is this 100 kilograms distributed. So, 100 kilograms will now distribute into, at equilibrium it is in the system. So, it will distribute into mass of A, it can distribute into mass of A in water plus mass of A in the solids. These are two, it can distribute in these two phases. Okay. Now, what is the mass of A in the water? It is concentration of A in the water at equilibrium, we will call this as rho A to E into volume of water plus WA3E into mass of this. Now, here is the tricky part here. Okay. Now, this M3 depends on what is the definition of WA3. Okay. WA3 is what is called as the loading. WA3 is the loading of A on solids. Now, for the reasons I just mentioned, it is convenient, this is MA divided by some M3. Now, this M3 has to be dry, because when you take it for analysis, and we will see what the analysis procedure is later in the next section, you will realize that if I take a soil or sediment sample, by the time I analyze it, the moisture content may be different, because water may evaporate from your sample in the container and it may change by 5%, 10%, because the mass does not remain the same. We do not want that. We want that all measurements to be based on the basis of some fixed thing, whether our reference point is the same, it does not change. Okay. So, for that reason it is convenient for us to use dry mass, which is why I think people also use it for wet moisture content also, but sometimes it is convenient to use wet. So, this problem is complicated because of that. Also, because when you do dry mass moisture content basis, moisture content goes beyond 100%. Fraction will go beyond 100, because you can have a lot of water, you can have more water than the solid. So, it's very nice when we say fraction, moisture content as a fraction, it is very nice for us to be upper bound is 1. Okay. People are very uncomfortable when you say 140% moisture content, they will say what is the meaning of 140%. So, it is confusing, that is why they use wet basis, so that everything is there, and this is a fraction of water in the solid is whatever something. So, it is usually below that. So, if you use dry basis for moisture content, it can go beyond 100%, and so there is nothing wrong in it, except that it feels odd sometimes for some calculations. So, anyway, so here, but loading is all the time the standard this thing is this definition, which means that here I have to put W3 dash, right, So, what is the definition of W3 dash? So, here we have theta is M2 divided by the moisture content M3 dash. Yeah. Now, we want the M3 dash in terms of the moisture content. Okay. So, typically what we are doing is we do not want M2 here anyway. So, we will calculate it the hard way. Okay. This is the definition, we will leave it like this. Now, we do not know either of these two quantities. We know this, we can calculate this, we will calculate that in a minute. Okay. But these two are unknowns, which means we need one more equation to fix this. So, since we are saying it is at equilibrium, so we use Ka32 star equals WA3 equilibrium by rho A2 equilibrium, which means that WA3 equilibrium equals Ka2 star into rho A2 equilibrium. You can do the other way also. You can also express this in terms of WA3 in both sides and substitute rho A2 in terms of WA3 also. That is also possible, but either way. But we are doing this for a particular reason, you will see why. Okay. So, now in this equation, if I substitute this back into this one, we get 100 kilograms equals rho A2 equilibrium to V2 plus K32 star rho A2 equilibrium into M3 dash, okay, which makes it rho A2 equilibrium into V2 plus. Now, Ka32, this is a wet solid, completely wet solid. So, Ka32 is KOC FOC, because we are talking about an organic chemical here, we are all talking about organic chemical, no inorganic chemicals in this discussion, in this particular problem. So, we have KOC FOC M3. Okay. You look at the units here for a minute. So, when you are doing this kind of calculation, sometimes you just want to make sure units are correct. So, the units on the left hand side are MA, dimensions MA. This is MA by L cubed, yeah. This is L cubed plus this is M of AC by M of 3 dash into M of 3 dash divided by this is KOC is WA3 again by rho A2 rho OC, sorry. Yeah, same. You can write star also. So, I have just mentioned equilibrium here, so I put equilibrium. You can write star, it is the same thing. There is no, it is just nomenclature, that is all. Whenever I write star, star is where normally we would write star. I would usually write it as star. So, this for some reason I wrote it as equilibrium. So, you can write this as star also, it is the same thing. There is no description, universal description, you can all write it as which means these are all at equilibrium, that is the only definition. But sometimes I will just write it as rho A2, this is not, if understood it is equilibrium, we just write it as that. Okay. Sometimes rho A2 star is also solubility, so we have solubility in this problem also, so that is why I kind of keep it separately. That is also equilibrium, this is all equilibrium, this is different equilibrium, that is different equilibrium. So, there is a lot of nomenclatural problems there, that is why I put E here. So, now, so here we see that if you look at the units here, this is L cubed, volume is L cubed, KOC is is L cubed by MOC. If you go back to the definition of KOC, the KOC is the WAOC divided by rho A2. This is the definition of KOC. If you recall our discussion into FOC. So, WAO3 is M of A divided by MOC, and this is M of A by L cubed. The denominator is the concentration, MA by L cubed. This is MOC by M3 plus FOC. So, MAC is cancelled, L3 by MOC is what? Is KOC. So, if you write dimensions like this, then you know if you are missing something. They have to add up, all the dimensions have to add up. So, this will cancel, L3, this will cancel with this, you have MA on the right side, MA on the left side. So, this is dimensionally it is consistent. Okay. Okay. So, we have this equation here, rho A2 into V2 plus KOC FOC M3. Okay. So, this is the water, all the water. Now, here you have two possibilities. Now, our system, we have say, this is where your definition of the problem becomes important, the way you want to see it. This is solids. So, this is really solids plus water. What we are in this problem, what we are saying is there is a continuum, there is this water and this water is connected to this water. Yeah. So, if you look at solids here, the solids are here and there is pore water here, and this pore water is connected to the water on top of it. So, material that is here can travel here, material that is here can travel here. So, it is when we are saying it is equilibrium, we are truly talking about equilibrium between the water and this thing. So, now I have to write this water is the water that is there inside the pore also. It is not just V2, that is 10 raised to 3 meter cube is not enough. I have to see this, take the water content inside the thing, because that is where the equilibration occurs first, and then it moves out, then it equilibrates further. Okay. So, transport part we will talk later, but right now what we mean by equilibrium is this entire system which consists of two components, which is solids and the water. And the water may be anywhere, it can be inside the liquid or there. So, this is our very broad theoretical equilibrium definition. Now, I can take this system. The reason I am saying this is true is if I can take this system, I can shake it. So, I get a big mixer and I mix the solids and I mix the pore water and the other water and the solid, everything together. It becomes one giant slurry. All the water is now seems connected, it seems more intuitively connected. But in this particular system, when I am saying it, solids are sitting there and water is on top of it, it looks as though the solids are a separate system than the water, but they are all connected. The water is a continuum that is going from the pore into the supernatant, the water here. Okay. So, we add all this water together in this number here. So, now this calculation, everything else is known, we know this, we need to calculate V2 dash and M3. So, that is the little bit of calculation that we need to do. So, we know that V2 dash is V2, which is the supernatant plus V2 pore. Okay. The V2 pore water, what do we know? We know that the M3 is 1000 kilograms. We also know theta is 0.5, which means the water content inside the pore, inside the solids is 0.5 into 1000 is 500 there is 500 kilograms of water inside the solids. Okay. Which means M3 dash is 1000 kilograms minus 500 kilograms. M3 dash is the M3 minus M2, which is 1000 minus 500 equals 500 kilograms. Is the problem I said 1000 10 raised to 3 kilograms? Is that what's given? 10 raised to 3 kilograms. Yeah. So, pore water is 500 kilograms, which is the volume of pore water is 500 kilograms divided by the density of water is 1000 kilograms per meter cubed. Small number compared to the volume of water, large volume of water. So, you may even neglect it if you do not think it is important compared to. So, usually, so this is an example, it is a test example, so numbers are off, can be really off, but in a big system like a lake or something, numbers are huge, solid numbers are very big, because the density of solids is 2.5 times that of the water, and the mass is very big. Okay. So, this is I think just an example, just to do example to do calculations. So, now this becomes 10 raised to 3 plus 0.5. You can ignore this 0.5 if you want, it is just a nuisance in your calculations. So, 1000 plus 0.5, 1000 0.5, you can say it does not matter, you can see the difference. I will say it is approximately equal to 10 raised to 3, but in some systems it may become very important, okay. Especially when you have a slurry and all that, it becomes important. So, you have to take that into account anyway. So, our volume is still 10 raised to 3 meter cubed. Yeah. Now, M3 plus you also know it is 500 kilograms. Okay. So, now we will plug in all these values in here, rho A2 so star equals 1000 kilograms divided by, now the value of KOC, log KOC is 4, KOC is 10 raised to 4 and the units are liter per kilogram. This I had mentioned this to you when we were discussing KOC. So, when we say log KOC, this number is always, the units are liters per kilogram, which means I convert it to 10 raised to 4 liters per kilogram into 10 raised to 3 liters per meter cubed. It becomes 10 meter cubed per kilogram, because I am working in meter cube kilograms, I do not want a liter in between. So, I will convert all of this to the same units. So, this is this. So, we now do the final calculation, this rho A2 star equals 100 kilograms divided by 10 raised to 3 meter cubed plus KOC is 10 meter cube per kilogram into FOC is 0.2. This is FOC into m raised to 3, it is 500 kilogram. So, this will be 5000 to 5000 into 0.2 is 1000 again. So, it is 2000 meter cubed. Is that correct? Just check the calculation once. Just check the calculation, check if this is right. I do not have a calculator. Yeah. Now you have a concentration of 0.05 kilograms per meter cube. The problem done. Now you have to check one thing, 0.05 kilograms per meter cube multiplied by 10 raised to 6 milligrams per kilogram into 10 raised to 3 liters per meter cube. What will this give you? What will this give you? 0.05 into 10 raised to 3 is 50 milligram per liter. So, this is your answer. So, rho A2 star is 50 milligrams per liter. Is there anything wrong with this answer? This rho A2 star is 50 milligrams per liter according to this calculation. What is rho A2 star? It's the concentration of A in water. So, what is the next thing you have to check? The reason I am asking you this, if you think the answer is correct, go back and check. What will you check immediately? Whenever you get concentrations of water, you check it, compare it against. I have given you data in the problem. What is the data? Solubility. Solubility I have given you as 1 milligram per liter, and we have calculated rho A2 is 50 milligrams per liter. Is it possible? Rho A2 star at equilibrium is greater than rho A2 star, solubility. It is not possible. You cannot have concentrations greater than solubility. So, what is wrong? Where is the mistake? If in these kind of problems, mistake can be in only one place. It can be right at the beginning where you, what is the fundamental calculation or the basis for all our calculation? The mass balance. So, something is wrong in the mass balance. So, what can be wrong with the mass balance? So, you have to think from using this statement as a clue. If this is true, what will happen? Concentration, if it partitions into water and solids, the water concentration is 50 milligrams per liter, which means, but the solubility is only 1, which means it cannot accommodate, the water cannot accommodate more than 1. So, where will the chemical go? In the solid, but the solid, this is equilibrium between solid and water. So, it cannot partition more than this. So, where does the rest of the chemical go? It will? It will? No, we are not. In this problem, we are not allowing evaporation. So, if it evaporates, that is a different issue. That is a big problem that we will see later in the course. But in this system, we only have water and solid right now, and we are at, yeah? No. Let me give you a clue. Pure solid, yeah. If you add solubility of, let us say, a particular salt is say 35 grams per liter, okay. I have a 1 liter water bottle and I add 50 grams into this. At the equilibrium, what will you find? If this is the solubility, 35 grams per liter, I have 1 liter water bottle and I add 50 grams of salt into it and I shake it and I make it to equilibrium. At equilibrium, what will I find? I will find 35 grams in the water and the rest of 15 grams as salt, pure substance. It does not dissolve, it stays as pure. So, the same thing has happened here. Now, you do this calculation, it means that it is not, water concentration is higher than solubility, which means it is not possible. some of it has to remain as pure chemical, right. So, now we redo the mass balance. So, now the mass balance is, we will get rid of this example. Is 100 kilograms is now V2 into rho A2 star plus M3 dash into plus Ma pure undissolved solid. So, but then how many we have now? 3 unknowns. Do we have 3 unknowns? How many unknowns do we have in this equation now? So, I will write this equation as rho A2 star plus M3 KOC FOC rho A2 star plus Ma pure undissolved. How many unknowns are there in this equation? Huh? Rho A2 star is now solubility. This is solubility. So, we have only one unknown equation. This is the only unknown that is there in the equation. So, this is known. That is our premise from the previous analysis, that we know that now its solubility, it goes to limit solubility, the rest of it stays as pure chemical. So, this is maximum, whatever is remaining stays as the pure substance. Okay. So, here we do the calculation again. You can do the calculation, the same numbers that we had before. So, it is 10 raised to 3 meter cubed into 1 milligram per liter. So, we do 1 milligram per liter into 10 raised to 6 milligram per kilogram into meter cube. This is 10 raised to minus 3 kilograms per meter cube. This is 500. Thousand one. Is 1 kilogram, so is 0.2 kilograms. Check this calculation. This is 1. That's 1, no? Yeah, this is 1. 1 kilogram in water, 1 kilogram in the solid. Rest 98 kilograms is in the pure phase. Okay. So, if I change the numbers, the volume of the mass of solid or the mass of volume of liquid, this balance will change entirely. So, this is a very artificial problem. In this case, what we are imposing in the problem is that we are not allowing any other contact, we are assuming that contact is happening between the pore water and the main water, everything is nice. We are not concerned really about how long it is going to take. In the time scale that this will happen, other processes may also happen. Okay. So, in a real scenario, what may happen is the following. Suppose I have a river, say I have a lake, I will take a river, it is even more complicated. Then I have sediment. Okay. Somebody, there is a boat carrying chemical, this chemical dumps, this barge dumps a large amount of chemical into the water, say a ton, 1000 kilograms. This happens often, right. You have an oil spill, a tanker carrying oil spill, tanker breaks, all the water comes into all the oil comes into the water. If it is heavy, denser than water, it will come down and sink on the top of the sediment. It will land on top of sediment and sit there. Now here, from here it starts, now river is flowing, right. The river water is flowing, and there is also air that is in contact with it. A lot of things are happening simultaneously. This chemical is now transferring from as it is coming down. So, after a period of time the barge is gone. So, you will only find so with time you are going to find this, but while this is happening, while a leak is happening, there is some amount of transfer that has happened to the water already, that is one. Second, the transfer will happen from the sediment to water over a period of time because the water is moving. Then it can also happen, transfer can happen from water to air if this is volatile, okay. And then this is also moving out, this is spreading downwards, all these things can happen. So, the system may never come to equilibrium as we speak in this problem, but it is driven by equilibrium. The mass transfer will happen because there is an equilibrium state, and we will come to that when we talk about transport. Okay. So, the equilibrium is important to. So, what is the equilibrium? If we are saying in this scenario that we may never achieve equilibrium, what is equilibrium then? What is the importance of equilibrium from an environmental point of view? So, what I am saying here is the concentration of rho A2 in the water here, if it will never achieve equilibrium, then why are we interested in equilibrium? It is a maximum concentration. It will what we call as worst case scenario. Why are we talking about worst case scenario? Because sometimes we do not know what is happening. We are not sure what is happening, then we at least can say this is the worst case scenario, nothing can happen beyond this, this is the worst. Okay. Even if I do not know any science, I do not know any transport phenomena, nothing, I do not know what is happening underwater, I know approximately what is the depth of water, I know what is the soil content, organic content, I can at least say what is the worst case scenario. So, then you can plan for a worst case scenario. For example, in the earlier problem, I know that a lot of it is still sitting as pure phase, it has not gone into the soil. What can you do is you can just take it out, you can just pick it out, the rest of it is very small, 1 kilogram, maybe it is not important, okay, very easy to handle later on. Suppose in the previous problem, if you find that this number in the water you find it as 50 kilograms and here you find it as 30 kilograms, then you have a problem because a lot of it is in the water and this thing. So, percentages are very high. So, then you have to deal with the water much more. So, the way we treat water will be different from the way we treat the solids and the pure chemical. Okay. So, the same kind of scenario can exist if this chemical is a mixture of what we call as if the chemical is denser than water and also lighter than water, which means you will have another layer here which is floating on the water, which can evaporate directly and it can also dissolve on this end. There is another layer here which is dissolving, and all complications, all kinds of scenarios can exist. Okay. So, the property of the chemical in terms of the partitioning, in terms of the solubility, in terms of density and all that is important in assessing, making a preliminary assessment of what we call as the worst case scenario. Yeah. This is usually how far you are from the worst case scenario depends on the other information in the system, what kind of, it is a flowing system or it is a static system. So, if it is a lake, it is not going anywhere, it is sitting there. Over a period of time you may reach equilibrium, but if it is evaporating also, then equilibrium may not go, it may not come to equilibrium, but you are also evaporating. So, you have to assess what is happening there. So, all these are so in the earlier problem I can add a third phase, I can add air. So, in this problem in this system here I can add a third phase, air, and the problem will change significantly. So, if I add and assume that there is a nice transfer between all the three phases. How well this happens is again, as I said, it may take a long time for it to happen, it may never happen, it may take an impractical amount of time that we do, but this is what we study, and we neglect, we can ignore some components. We say it will take 1000 years for this to move into air or anything, so let us not consider air at all, we will just look at water and solids and that be done with it. Okay. And that depends on this mass balance, the worst case mass balance, that you say that 0.5% is in the air, 60% is in the water, and 49, 48, 38% is in the sediment. You will ignore the air, so that is not important, I will just not even bother about it. Let us not worry about air pollution now, we will worry about the water and the other two things. So, this is quick decision making from a regulatory point of view, that is useful. So, simple mass balance is like this. So, if you are writing three systems like this, we can write again 100 kilograms equals mass of A in water plus mass of A in solids plus mass of A in air plus mass of A pure undissolved, and you can add any other phase. If there is something else there, you can add that also. Okay. So, this will constitute the worst case scenario distribution. So, this is a very important concept people talk about in freight and transport. This is the first analysis people do, they have information. Now, this is not as simple as it looks here in environmental systems, because for example, as an example I mentioned, in river systems it is not static, the volume of water is changing, because as dissolution is occurring, your carrying system is changing its volume, right. So, then we have to take a different approach to it, we can't use this kind of approach. But in systems like lake and groundwater, systems are not moving very fast or are not moving at all. So, you can do this kind of analysis, and definitely for air you can't do it at all, because air is not static, air is changing, air is constantly moving. So, it is very impractical for me to look at air here, but this system what we have just written here is very valid for soil, unsaturated and saturated soil. So, this entire system I can say is all inside soil. I can take a system where I have saturated soil and unsaturated soil. Among these two, I have all these three phases, I have soil, solids, I have water, and I have air. So, within this system there is not much movement, you can assume that equilibrium may be achieved in a reasonable amount of time before it gets to the surface and starts moving out. Okay. So, the system definition has to be done properly, and that is a big challenge, and that requires experience of knowledge of the environmental system itself. So, you can't arbitrarily take air, and the next problem that will come if you are taking air, outside air, if I am taking, this is land and air, if I dump 1000 kilograms of material on the road somewhere, if I want to calculate what is worst case scenario, what will I take as the volume of air? I have no idea. Volume of air, I can take 1 kilometer height, 2 kilometers height, 50 kilometers height, it is unbound, right, and there is boundaries to that, but we will discuss that later. But that is also moving, okay. My scope of reference is changing constantly. So, we do not deal with this kind of problems in that sense there, we approach it differently. So, but this is useful in certain scenarios and for certain kinds of decision making.